The topic of this video will be the E2 reaction. The E2 reaction is a second-order elimination reaction. The E stands for elimination, and the 2 stands for bimolecular, meaning that 2 molecules are involved in the rate-determining step. The general reaction for an E2 reaction looks the same as an E1. The substrate needs a good leaving group, and the carbon adjacent to the carbon with the leaving group needs to have an abstractable proton. The reaction also requires a base. Loss of the leaving group and the proton produces an alkene as the product, along with the conjugate acid of the base and the leaving group. The mechanism is where the difference from E1 can be observed. Just like with SN2, this is a single-step mechanism. The base abstracts the proton, the electrons from the carbon-hydrogen bond form the pi bond, and the leaving group leaves, taking its bonding electrons. Just like in SN2, this is a concerted mechanism, meaning all of these steps happen at the same time, producing the alkene product. Now let's look at an example reaction. This substrate can react with sodium ethoxide to produce this product. The mechanism occurs in a single step, with the sodium ethoxide deprotonating the substrate to produce the alkene product. The ethoxide ion deprotonates on the carbon next to the carbon with the leaving group. The bonding electrons to that proton form the pi bond, and the leaving group leaves with its bonding electrons to give the alkene product. Because there is only one step in the mechanism, this must be the rate-determining step. Both the substrate and the base are involved in the rate-determining step. It is bimolecular. Therefore, the structures of the substrate and the base affect the rate of an E2 reaction. A strong base speeds up the rate of the E2 mechanism, therefore favoring it. See the same substrate preference for E2 that we saw with E1, where tertiary substrates react more quickly than secondary, which react more quickly than primary. This reflects the stability of the more substituted alkene product, and therefore the more stable transition state. Again, remember that methyl substrates cannot react in elimination reactions because there is no proton on a carbon next to the carbon with the leaving group.